Hello everyone, welcome to SS Talks Chemistry. I hope you all are doing great. So we were discussing our previous year questions of the CSIR NET exam, and in that the unit we have started, that was the thermodynamics. Right. So two of the parts in this we have already discussed. Now this video is gonna be the part number 3. So if you have not watched the previous two parts, playlist I have made on the channel where we are discussing the all the questions of the CSIR NET exam, previous year questions, so that you can check it, or I'll provide in the link in the description. Even from that you can get the access to that. Okay, so let us begin with this part now. So this question, it says a sample of 2 moles of the oxygen at 500 kelvins is expanded from a volume which is of the 5 liters to the 50 liters volume. So basically oxygen is given, that is your diatomic gas. So O2, which is my diatomic gas, it is given to us. Its number of the moles is also given to us, which is 2 moles of it. Right. Now the volume V1 it is given, that is 5 liters. It is going to the volume V2, which is 50 liters. Now under the adiabatic and the reversible. So condition is adiabatic. Adiabatic, it means Q value in this it is gonna be a 0, and the process it is reversible in the nature. Reversible means slowly this process has been carried out. So now when our process is reversible and the adiabatic, we follow the equation which is called as the Poisson's equation. Right? So these values we can obey. These equations we can obey. So this is the data that we are getting from this. So the change in the internal energy in kilojoules is closest to. So according to the first law of thermodynamics, first law of the thermo, we know that delta U it is Q plus of the W. Now Q here it is 0, delta U it is W only, delta U it is NCV into the dt of it. So delta U is NCV into the dt of NCV into the dt, or it is NCV into the T2 minus of the T1. Right. Now number of the moles it is given to us. CV we can find it because the gas it is given, that is diatomic. For that gamma value you will be knowing, from that CV value you can find it out. Now T2 minus of the T1. One temperature it is given, that is 500 kelvins. The other temperature we are not having. So since the condition it is adiabatic and the reversible one, making use of the Poisson's equation, that is relating your temperature and the volume, which is because that is given to us, we can find the other temperature, and from that we will be finding our internal energy change that we are getting in this. Right. So let us begin with this now. Okay. So now according to my Poisson's equation, that says PV gamma minus of V1, it is constant. Right. So T1 V1 gamma minus 1, it is T2 V2 gamma minus of the 1. Right. So from this T2 it will be T1 into the V1 by the V2 raised to the power of gamma minus of 1. First temperature it is 500 kelvins. Initial volume it was 5 liters. The final it was 50 liters. So 5 upon the 50. Now the gas it is diatomic. For the diatomic gases, the gamma, which is ratio of the Cp upon the Cv of it, this ratio we have, that is 7 by the 5. Right? Because in this Cp value you have, that is 7 by 2R, and the Cv value it is 5 by 2R of it. These are the values. So here it will become 7 by 5 minus of 1. So it becomes 1 by the 10 raised to the power of 2 by 5, right, into the 500. So just solve this and find the temperature, which is your T2. So on solving this T2 we get it as 199.05 kelvins. So this is my T2. Okay. So now delta U we have to find it. Delta U that was equal to N into the CV into the T2 minus of the T1. Number of moles we are having is 2. PV value it is 5 by 2 into the R of it because it is diatomic gas. T2 it was 199.05. The temperature that we calculated. The initial it was 500 Kelvin. Just solve this, substitute this value of the R. You need to find it in the units of the, that is kilojoules, right? So it will be 8.314. The units it will be joule per mole per Kelvin of it, right? So now here 2 moles it was there. So this mole unit we are having, and this temperature difference it is gonna be in the Kelvin, 199.05 minus of the 500. So this is again in the Kelvin. So units here you see with this mole, per mole is getting being cancelled. This per Kelvin and this Kelvin is being cancelled out. Overall, in the joules we are getting divided by a factor of the 1000, we will get the answer in the units of the kilojoules. Okay, this joule I am omitting from here. So here on solving this, we get the value as minus of the 12.5 kilojoules of it. So this is gonna be the answer in this. Okay. So based upon this, the correct option minus of 12.5, option B, it becomes the right answer. Okay. Next, this question now. Consider the entropy change in a system undergoing the transformation as depicted in the diagram which is shown below. So here what is happening? You are at a temperature that is 25 degrees centigrade, which means it is my 298 Kelvins. Right. From 298 I am going to 50 degrees centigrade, which is my 323 Kelvins. In that, the entropy change that I am having, that is delta S1. This is delta S1. Now from 50 to 75, that means 75 degrees, that means to a temperature of 348 Kelvin I am going. So this from 50 to 75, the temperature that we are going, the entropy change in this case it is delta S2. Okay, and one way we are going is we are going from 25 to 75 directly we are going, and the entropy change in that case it is delta S it has been given to us, right? So now based upon this, the relationship between these entropy values is being asked to us, right? So now I know one thing, that the entropy, it is your state function. It is my state function. That is, it is independent of the nature of the part. It is independent of the nature of the part. Nature of the part. Right? So it is dependent only on the initial and the final state of the system. So in both these processes, we are starting from 25 and going till 75. But the path routes you have followed is two different. First is directly you are going from 25 to 75, and the second way is firstly from 25 to 50 and then to 50 to 75. So it is not dependent upon the nature of the path, which means the entropy change that is we are in this system that we are getting in going from 25 to 75, this is gonna be equal to the sum of the entropy changes in going from 25 to 50 plus the entropy change in going from 50 to 75. So this relationship it is gonna be there, right? So based upon this, the options if you see, delta S versus says delta S is not equal to this, it is the incorrect. Second one is also saying it is not equal, again the incorrect. So from this two options we have eliminated. Okay. Now we have to find relationship between the delta S1 and the delta S2. Which among this is the greater one or the smaller one, or both these are the equal or the different. Now I know that the entropy change it is equal to NCV ln of the T2 upon the T1 plus of the NR ln of the V2 upon the V1. This relationship I know. So if I take at constant volume, that means delta S it is gonna be equal to NCV ln of the T2 upon the T1, T2 upon the T1. That means if I take the ratios of this, I'll be getting the values of delta S1 and the delta S2. So let's do that. In 25 to 50, if we are going, this is in the Celsius, this entropy change it is delta S1. So delta S1 it is gonna be N into the CV ln of V. Now final temperature it is 323 Kelvin. The initial it was 298 Kelvins of it. On solving this we are getting the value which is 0.080 N CV of it. This is N into the CV. This is what we are getting. And in the second process where we are going from 50 degrees to 75 degrees, the entropy change it is delta S2. So delta S2 it is gonna be NCV ln of the final temperature it is 348 Kelvins upon the 323 Kelvin. On solving this we get the value which is 0.074 into the NCV of it. So from the values you can clearly detect that delta S1 it is greater as compared to the delta S2, right? So we can say delta S1 is greater than the delta S2 and overall delta S it was equal to delta S1 plus of the delta S2. So these two conditions are there. Okay. So now based upon this among 3 and 4 if I see fourth one it says delta S1 is greater than the delta S2. Option 4 will be the right, that means the option D to be the correct answer in this. Okay. So D is the right answer for this question. I hope it's clear. Moving to the next one. This question now. The molar composition of a mixture of the P and the Q at equilibrium is 3:1. Molar composition means there about the number of the moles this ratio has been given. That says number of the moles of the P to that of number of the moles of the Q. This ratio is 3:1. And P is the number of the moles of the P and NQ is the number of the moles of the Q. This value has been given. A small disturbance if it is caused in the composition, it results in the change in the chemical potential of the P by a value of 10 joules per mole. Okay, so what is the chemical potential of the Q that is gonna change? Okay, so this change in the chemical potentials with the composition, we make use here the Gibbs-Duhem equation. We use the Gibbs-Duhem equation. According to this Gibbs-Duhem equation, we know that N1 into the d mu1 plus the N2 into the d mu2, this is equal to the 0. Now instead of the 1 and 2, now the terms are P and Q because this mixture we are having. So we can write NP into the d mu P plus of the NQ into the d mu Q. This is equal to the 0, right? From this I can get that NP into the d mu P it is equal to minus of the NQ upon the into the d mu of the Q, it will be there, right? From this the ratio that is given we can obtain it, which is NP upon the NQ. This is equal to minus of the d mu of the Q upon the d mu of the P, it will be there, right? So now this ratio of the number of the moles it was given to us, which has the value of 3 by 1. So this is 3 by the 1, and the change in the chemical potential of the P value it has been given, that is 10 joules per mole of it. So here it is 10 joules per mole of it. This change in the chemical potential of the Q we have to find it out, right? So d mu Q it is gonna be minus of the 30 joules per mole of it. So this is gonna be the answer. Okay. So that means the correct answer is the option third one. So you see here the sign is also important. You have the value of the plus 30 and minus 30 value is also there. If you neglect the negative sign, it will give you a negative mark in the exam. Right? So correct answer will be the option C, not the A in this. So sign is also important. Okay. Next, this question now. The question it says 1 mole of a perfect monoatomic gas is put through a cycle which is shown as below. Okay. So we are going from A to B, B to C, C to D and D to A. The total amount of the work done during this cyclic process. Okay. So total work done, we are gonna break these processes. So it will be work done in going from A to B plus the work done in going from B to C plus the work done in going from C to D and plus the work done in going from D to A. D to A. Okay. The plot is for the P versus the B. Here the volume it is given. Now this is the volume and that is in the liters we are having it. Okay. So here now these processes, firstly I have to find the work done. For this process, firstly, that is for the D to A if you see. D to A if you are seeing. The volume here it is kept to be the fixed vector. Right. We know that work done it is minus of the P external into the dV of it. If dV is equal to 0, then work done it is gonna be 0 only, right? So from the D to A if we see it, then the dV it is 0, so work done in this process it is gonna be 0 only, right? That means remaining three processes that I am having, their work done is gonna contribute to the total amount of the work done, right? So now step by step find the work done. So work done in going from A to B. So in A to B process, external pressure we are having that is of the 2 bar pressure it is there. The volume change. We are going from 23.24 to the final volume which is 46.48. Right? This is what the volume change we are getting. So work done will be minus of the 2 that is in the 2 into bar we are having into the volume change which is 46.48 minus of the initial volume which is 23.2, right? So here we get minus 2 into the 23.24. The units will be liter bar of it, or it is gonna be 46.48 with the negative sign, liter bars only. So this is the work done in the process A to B, right? Now the next process we are gonna discuss just like the A to B, it is for C to D if you consider. Now the pressure it is 1 bar in this case. The volume change that we are observing in it, this was the volume. The volume change it is 92.96. From this you are going to a volume which is 23.2, right? So this is gonna be the volume change. So work done in the process which is from the C to D, it is minus of the 1. The volume change, finally we have gone to 23.24. Initially it was 92.96, right? So this was only the volumes. So on solving this, we get the work done that is gonna be 69.72. So this is gonna be positive because volume change it is negative and negative becomes the positive. So the units again is gonna be liters. Right. Now we are left is with the work done in going from B to C process. Right. So B to C plot if you see B to C plot. Now it is PV plot. This type of the curve you observe when you have the isothermal conditions. So this process it is my isothermal in the nature. Right. These processes from A to B and C to D, these were isobaric. These were isobaric processes. And this B to A process, it was isochoric because the volume it was kept to be the fixed values, right? So now for the isothermal processes, work done is equal to minus of the nRT ln of the V2 upon the V1, right? But now here in the question you see temperature we are not having. It is just the moles has been given and the cyclic process it is taking place. no temperature conditions has been given. So we know the gas, it is ideal in the nature. For the ideal gases, this PV is equal to the nRT, right? So minus of the nRT can be replaced with the minus of the PV in this ln of the V2 upon the V1. Okay, so now here the pressure and the volume, you are gonna keep the final pressure and the volume that you are reaching, that is to the C process, because we are starting from the B and we are reaching to the C. The final pressure and the volume that we are having, which is of the 1 bar and 92.6 as the volume, this you have to keep it. Okay, so now this will become minus of the 1 bar. The volume, it was 92.96 ln of B. Now the final volume from the B, we are reaching to the C. C is 92.6, B is 46.48. So this is gonna be ln of 92.96 upon B, that is 46.48. 46.48. So this is gonna be the work done. So this value, if you see, it is gonna be ln of the 2 we will be getting. So it will be ln of 2 into the minus of 92.96, which gives us the work done value, which is minus of 65.07 of it. Right? So now again the unit, that is gonna be a liter bar only. So now all the processes, the work done we have calculated. So total work done, that was equal to work done in going from A to B plus of the B to C plus of the C to D plus of the B to A. This was 0 plus of. Now for A to B, the work we have calculated, that was minus of 46.48, right? For the B to C, we have calculated it as minus of 65.07 plus of D. Now for the C to D process, the work done we calculated, that was 69.72. 69.72. Right? All this is gonna be in the units of the liter bar. So we are getting the value, that is gonna be 41.83. This is minus of this in the units of liter bar of it. You have been asked to find in the units of the, that is in the joules we have been asked to find it out. Okay, so let's do the conversion now. 41.83, this is in the liter bars. You want it in the joules, so multiply it with the 8.314 joules per mole per Kelvin. Okay, and divide it with the R value, that is in the units of liter bar, which is 0.08314 liter bars per mole per Kelvin. Per mole per Kelvin. So the units, if you see, mole per Kelvin and mole per Kelvin is getting being cancelled out. Liter bar and liter bar, this value it becomes to be the 100 over here. So the work done you are getting in the units of the joule now. So that becomes 4183 joules of it. This is gonna be the total amount of the work done. Okay, so this is how this question it was to be solved. So based upon this, the correct answer becomes the option second one. Okay, so this is your right answer. I hope it's clear. Now the next this question we are having, Cp minus Cv for a non-ideal gas, that means a real gas. It differs from a Cp minus Cv for a perfect gas. Perfect gas means the ideal gas. Okay, by which of the following expressions it is gonna be differentiating. We know Cp minus Cv, that is for the ideal gas. For the ideal gas, this is equal to the Nr. Nr, if N you consider it to be the 1, if N is 1, then the Cp minus Cv for the ideal gas, this is gonna be equal to the R only. Right. Now for the non-ideal, that is for the real gases, Cp minus Cv for the real gases. So here you see it is in the units of del P by the del T at constant volume, del V by the del T at constant pressure. So in that term, Cp minus Cv relationship, we have to write it. A number of the equations we learn that defines the difference between these two. We have to choose this one in which these expression we are gonna get. So Cp minus Cv, we know it is temperature into the del P by the del T at the constant of the volume into the del V by the del T at the constant of the pressure. So this is the value of Cp minus of the Cp. If I see the difference between these two, I'm not reaching to the final expressions which has been given to me. Right. So what I have to do is I have to make some of the changes in this. Right. So the next expression you see in the given options, it is for the del U by the del V at constant of the temperature or del U by the del T at the constant of the pressure. So these values, which is del U by the del V at constant of the temperature, using my thermodynamic equation of the state, I can get that. Right? I'll be using the first thermodynamic equation of the state and will be substituting it. Okay? So, using the first thermodynamic equation of the state, we have that my del U by the del V, we know that del U by the del V at the constant of the temperature, this is equal to temperature, it gives us the value of the pressure. So it is del P by the del T at the constant of the volume minus of this pressure. Right? So this is from the first equation. So we know this thing. From this you can find the value of this, which is del P by the del T at constant volume, and substitute that in the given this expression. Okay. So these equations you can number it. This is equation 1, this is equation 2, this is equation 3 we are using it. So from this we get the pressure plus of the del U by the del V at the constant of the temperature. This upon the 1 upon into the 1 upon T. This is gonna be the value of del P by the del T at the constant of the volume. Right. So put 4 in the 2 now. So put 4 in the 2. We get that the value of this Cp minus Cv of the real gas, Cp minus Cv for the real gas, this will become temperature. So here the value it was 1 by T into the del U by the del V at the constant of the temperature. This is the volume. Okay. Plus of the pressure, and this was into del V by the del T at the constant of the pressure. So this is what we are getting. So this 1 by T and this T value it will get cancelled. So we are getting del U by the del V at the constant of temperature into the del V by the del T at the constant of the pressure plus of the pressure into the del V by the del T at the constant of the pressure. This value we are getting. Right. Again, you see, if I'll be doing the difference, still I'm not gonna reach over here because only two of these terms these are present at max, or in just one options I am having the factor of 1 by t along with these two. So that means again I have to do some of the substitutions so that this term it is gonna be eliminated somehow, right? So what you do is the ideal gas you are having, for that PV is equal to RT considering 1 mole of the gas. So volume here it is RT upon the P of it, right? So find the value of del V by the del T at the constant of the pressure. So we have del V by the del T at the constant of the pressure. This is del by del T of RT upon the P. This differentiation we are doing at constant pressure. So R by the P they are constant, so they will come outside. It will become del T by the del T at the constant of the pressure. So del T by the del T it is unity only. So this value it is R upon the P. Right. So this equation you can label. So this was question number 4 we did. Then this is the fifth one we can do it, and this we have got the sixth expression. So substitute 6 in the 5, 6 in the 5, we are getting Cp minus Cv for the real gas. This is gonna be del U by the del V at the constant of the temperature into the del V by the del T at the constant of the pressure plus of the pressure term into this value into the pressure. Now substitute here the value R by the P. So this P and P term it is getting the cancelled over here. So this is what we are getting, that is for the real gas. Del U by the del V at the constant temperature into the del V by the del T at the constant of the pressure plus of the R. Right. So now we needed to find the difference between the deviation. It means the difference between these two we have to find, which is for the ideal and the non-ideal. So just do that. So Cp minus of the Cv, that is for the real gas, minus the Cp minus Cv, that is for the ideal gas. Right. So this value we have got it as del U by the del V at the constant of the temperature into the del V by the del T at the constant of pressure plus of the R, right, minus Cp minus Cv for the ideal gas is also the R only. So this R and this R it will get cancelled. So difference we are getting, which is del U by the del V at the constant of the temperature into del V by the del T at the constant of the pressure. So this is the difference. So you can see now I am reaching to my options. Right. So we have got is del U by the del V at the constant of the temperature, that is given to me in this expression, and in this expression it is given. So here at constant pressure they have taken, this can't be there, and del U by the del P I have not taken. Right. Del U by the del V at constant of the temperature into del V by the del P at constant pressure. This is given to me in the option B. In the C, this minor 1 by T term has been included, so this is obviously incorrect. So my correct answer is gonna be the option B in this case. Okay, I hope it's clear. Moving to the next one. This question we are having a monoatomic. So type of the gas it is given, that is monoatomic. It is monoatomic gas. It undergoes the expansion from the P1 V1 to the V2 V2 under the isothermal or the adiabatic conditions. It can go the expansion. I know that. The pressure of the gas it is gonna fall more rapidly under the adiabatic conditions. Why is it so? Because in the adiabatic conditions, considering the process to be reversibly adiabatic, we know PV gamma it is constant, right? So we see that pressure it is inversely proportional to V raised to the power of gamma of it. Now my gas it is monoatomic. So atomicity, that is gamma, which is ratio of Cp by the Cv for the monoatomic gas. This ratio is 5 by 3. So pressure is gonna be inversely proportional to the volume, which is raised to the power of 5 by 3 of it. So this value it is there. Okay. Due to that, it is following more rapidly. Alright. So PV is inversely proportional to V raised to the power of 5 by 3. Option D, in that we are having this. So D becomes the right answer. Okay. Next, this question now. For a van der Waals gases, the partial derivative, which is of the del U by the del V at constant temperature. So this is from the first thermodynamic equation of the state, and this gives me the value of the internal pressure. This is internal pressure, and this pressure it is nothing, it is your correction term, that is the correction term, that is of the pressure in the van der Waals gas equation. In the van der Waals gas equation, the value for this it is A n square upon the V square. Considering the 1 mole, it will be A by the V square. So this is the value. Okay. So if you know the concept behind this, you could have easily done this without solving it. But I'm gonna tell you the complete derivation part of it. You will be seeing that same answer you are gonna get in this. Okay. So I have the van der Waals equation, the van der Waals equation, that is P plus of the A by the V square into the V minus of the V this is equal to the RT considering the 1 mole of the gas. Okay, so now del U by the del V. So using the first thermodynamic equation of the state, we have this del U by the del V at the constant of the temperature. This is temperature into the del P by the del T at the constant of the volume minus of the pressure. This thing we know it. Using the van der Waals equation, you have to find the value of del P by the del T at the constant of the volume. So let's do that. So P plus of the A by V square into V minus the B, it is RT, multiply this, open up this bracket. We will be getting PV plus of the PV minus of the PB, it will be there, plus of the A upon the V, it will become, or you can take this on the other side, it's better to do that way. So it is P plus of the A upon the V square, it is RT upon the V minus of the B of it. So from here pressure we are getting, that is RT upon the V minus of the V plus of the A upon the V square. So now del P by the del T at the constant of the volume, this is gonna be del by del T of the RT upon the V minus of the B minus of the A upon the V square. So this thing we are having, this differentiation we have to do it at the constant of the volume. So first this R upon the V minus B, it is constant, into the differentiation with respect to the temperature, that is gonna be 1. So it is R upon the V minus of B minus of A upon the V square. So now this differentiation you have to do it. This is done at the constant of the volume, which means A is also a constant and V is also a constant. No temperature term it is there. So this is gonna be 0 only. That means the value we are getting, which is R upon the V minus B of it. Now in the expression of the first thermodynamic equation of state, just substitute that del U by the del V at the constant temperature, it was temperature, into the del P by the del T at constant of the volume minus of the pressure. So here this temperature we are getting, del P by the del T, this value we have calculated, which is R upon V minus of the B plus of minus of this T. So you see here this value, which is RT upon the V minus of the B, this is equal to this value, which is P plus of the A by the V square minus of the P. So this pressure and pressure term, it is getting being cancelled out. So we are getting the value, which is A upon the V square, right? So this is the internal pressure for the van der Waals gases that we are getting, right? So this is what I told you also, that you are gonna get this answer only. So again, the proof of it I have also given. Okay, that makes the option C, which is A upon the V square, to be the right answer. Got it? Next, the excess molar entropy of a mixing of a liquid A with the liquid B. Now here in the previous one more question, it was the that we did discuss previously. There it was excess of the molar Gibbs free energy. Now here it is excess of the molar entropy. So excess of the molar entropy. That means the units of this, they are joule per mole units you are having. This is equal to the change in the entropy of the mixing that you get through the experimental methods minus the delta S of the mixing that is done through the theoretical methods. This difference between them, it gives us this excess value. Okay. So now here from this delta S of the mixing, which is for the experimental methods, this is gonna be equal to delta S of the mixing that we get by a theoretical method, that is using the formulas which we calculate, plus of the excess value of it, excess delta S of the mixing that we have it, right? So now this value is also already given to us, which is excess of this value, which is minus of the R ln of the 2, it is given to us. This value it is minus of the R ln of the 2. The experimentally observed change in the entropy upon the mixing 1 mole of the liquid A with the 1 mole of the liquid B is gonna be. So this value we have to find it out. Now we need is this theoretical value so that we can find this experimental one. So this theoretically value, we know the formula for this, delta S of the mixing, obtaining it theoretically. So it is now molar entropy, molar one. So this is gonna have the formula which is gonna be minus of the R summation of the xi into the ln of the xi, ln of the xi, which means summation means the sum of it. So units you will be seeing you are gonna get in the units of joule per mole only. So R value, if you see, it is 8.314 in the units of joule per mole per Kelvin we are having it. Right? Yes, we have it. Now into this is gonna be x1, that is for the liquid A, into the ln of the xa. These are the mole fractions. So ratio of the moles, it is gonna be there. That is gonna be your unitless quantity. Okay, plus of the xb into the ln of the xb, it is gonna be there. Right? So you are seeing that we are getting in the units of the joule per mole term only you are getting the entropy value. Okay. So this is the what the molar entropy it means. Now number of the moles is known to us. Just substitute these values in terms of R only we have to find it. So I'm replacing this value with the R. So it is 1 upon the 2 ln of the 1 upon the 2 because 1 moles of each it is given to us. Xb is also 1 by 2 ln of the 1 by the 2 it is there. So this value it becomes minus of the R into the ln of the 1 by 2, right? Or we can write it as minus of the R into minus of the ln of the 2 of it. So minus minus it will become plus. So it is R ln of the 2. So this is the entropy of the mixing that you are getting by a theoretical method. So here that means this value we have obtained it as R ln of the 2. So the difference we are getting which is of the R ln of the 2 minus of the R ln of the 2 only, that is gonna be 0. So this is gonna be the answer. So that means experimentally that gives the energy of the mixing that you are getting, it is 0. Option C is the right answer in this. Okay. Next, this one, the change in the chemical potential of 1 mole of the ideal gas when it is compressed isothermally at 300 Kelvin from 1 atm to the 2 atm it is closest to. So now we know chemical potential it is mu naught plus the RT ln of the P it is given. This expression we have. Now at two different pressure conditions we have to find this. We are having this chemical potential and their change we have to find it out. So we can say that mu1 it is mu naught plus of the RT ln of the P1, right? And the mu2 that is chemical potential at the second pressure condition it is mu naught plus the RT ln of the P2, right? So now the difference between these two, that is my mu2 minus of the mu1, that is gonna be mu naught plus the RT ln of the P2 minus of the mu naught R plus of the RT ln of the P1. So this value it will become, so this mu naught and mu naught it is getting being cancelled out. It becomes RT ln of the P2 upon the P1 of it. So these values now they are known to us. Just substitute their values. It is 8.314 joule per mole per Kelvin, right? Temperature it is given that it is 300 Kelvins, right? ln of. Now the pressure P2 it is 2 atmosphere and the initially it was 1, right? So the units here you see per Kelvin and this Kelvin unit is getting being cancelled out. We are getting the answer in the joules per mole. We are getting the answer in this case, right? So that is gonna be, so ln of the two values also given, that is 0.69. Just multiply that and you get your answer, that is 1720.998 joules of it. This is gonna be the value in this case. So close to this one, I can see it is in the 1725. Option B becomes the right answer. Okay, moving to the next one. This now that gives free energy for a regular binary solution of the components A and B at the temperature T on the basis of the Margulis equation. Okay, so for the activity coefficient S. So which of the following is the true one? So one way we write the delta G mixing, that is for the ideal gases. We write it like this na, RT into the summation of the Xi into the ln of the Xi. Like this we write it. For the binary solution means two of the components are present. It will be RT into the X1 into the ln of the X1 plus of the x2 into the ln of the x2, or the components A and B in terms of that we can write it. So it will be xa ln of the xa and the xb ln of the xb. This way we can write it. But this is for the ideal gas, ideal solutions you write this for. For the real solutions, for the reals one, that for this equation is used, which is called as the Margulis equation. In this case, delta G of the mixing we have, that is RT into the XA ln of the. Now here instead of the XA you write it gamma A into the XA of it. Gamma is the activity of this. Okay. Plus of the XB into the ln of gamma B into the XB of it. Like this we write it. Okay. When you open this brackets, it will be RT XA ln of the XA plus of the XA ln of the gamma A. Like this it will be there, plus of the XB ln of the XB plus of the XB ln of the gamma B it is there, right? So this value, which is ln of the gamma A, this is equal to xb square into the Margulis coefficient, which is this xi value. Okay. Similarly, ln of the gamma B value, it is equal to xa square into this coefficient, which is Margulis constant that you say xi over here. So substitute this in your this expression now. So my delta G of the mixing, it will be equal to RT into the ln of the xa into the ln of the xa plus of the xp ln of the xp we were having, plus of the xa times ln of, instead of the ln of the gamma A, this value now you substitute, which is your xb square into this Margulis coefficient plus of the xb. Now ln of the gamma B, we have the value which is xa square into this Margulis constant. Okay, so from here you see it is RT xa ln of the xa plus of the xb ln of the xb plus of the. Now from both of this you can see we can find the value xa into the xb and xa into the xb to be the constant, xa into the xb into this constant value into the xb plus of the xa. Now here only the binary solution we are having. This is gonna be the ratios of these fractions only we are having, which is the mole fractions we have. Their sum it is gonna be equal to the unity only, right? So which means the delta G of the mixing that you have, this is equal to RT into the XA ln of the XA plus of the XP into the ln of the XP. Now additional factor in the real solution that is added, which is XA into the XB into this Margulis constant. So this is gonna be the complete value of the delta G of the mixing as per this equation. Okay, that makes the option for the n number of moles if we are having, so we'll multiply that with the factor of the n also. So xa ln of the xa plus of the xp ln of the xp plus of this xi into the xa into the xb, option B will be the right answer in this case. Okay, I hope it's clear. So difference is there for the ideal solutions and for the real solutions. For the real solutions, this equation we have to obey. moving to the next one now. So now the next one we are having, that is this question. It says during the phase transition, that is at a constant temperature. The condition is of the constant temperature of a solid from the one form to the another. The change in their molar volume that is given to us, it is independent of the pressure. The change in the molar gives free energy in the units of joule per mole when the pressure it is increased from 1 bar to 3 bar pressure it is. Okay. So now related to the gives free energy, suppose I'm not having any idea how we have to proceed. So go from the basics. You have your Maxwell square like this. It is good people have studied under very amazing teachers, right? So now for this Gibbs free energy, so dg we can write it that is equal to vdp minus of the s dt of it. Now go from the statement the conditions that are given. So it is at constant temperature, which means dt value will be 0 at the constant temperature. Dt will be 0. So we say that dg it is vdp only. Right. Now the condition it is given, the change in the molar volume. Change in the molar volume means delta V value it is given to us. That means about the change we have to talk it to consider the change on both the sides. So d of the delta G it is gonna be delta V into the dp of it like this. Now they are saying that the pressure it is increasing. So pressure is changing in this case. We have to find the change in the molar Gibbs free energy. So what you do is you integrate on both the sides because there you are having the small change. Complete change you have to find it. So integrating that will be helpful for us. So integrate on both sides. Okay. So here we will be getting integration of d of the delta g that is equal to delta v into the dt. Pressure is changing from the P1 to the P2 of it. So on solving this, I am getting delta g it is delta v into the delta P it will be there, which is P2 minus of the P1, right? So this is how I proceed when I'm not knowing that how I have to proceed it. What you can follow it. Go from the basics, okay, and keep on following the statements which are given in the questions. From that, keep on applying these conditions which are given to us. Okay, so delta G. Now you can see delta V value it is given. P2 minus P1 is also given. Delta G that is change in the molar Gibbs free energy. I can find it out very easily, right? So the units are it as 1 centimeter cube per mole, right? Now pressure here it is from 1 to 3 bar, so it will be 3 minus of 1 units it is gonna be the bar, so it is 2 per mole centimeter cube and the bar pressure it is given. Alright. Now you need to find in the units of joule per mole. So rest is just remaining is the unit conversion that we can easily do it. So we got the value which is 2 centimeter cube bar per mole of it. So firstly I am converting this centimeter cube to the liters of it. We know 1 liter is 1000 centimeters cube of it. So 1 centimeter cube it is gonna be 10 raised to the power of minus of 3 liters of it. So it will be 2 into 10 to the power of minus of 3 in the units of liter bar per mole. Right. Now to convert it into the joules per mole, multiply it with the R factor which is 8.314, which is joule per mole per Kelvin, upon which units I have to remove it, that is of the liter bar. So it is gonna be 0.08314 liter bar per mole per Kelvin, per mole per Kelvin. So per mole per Kelvin will get cancelled. Liter bar and liter bar will get cancelled. So finally here per mole and joule it is left. So units it will come the joules per mole. This we get as the 100. So we are getting 2 into 10 to the power of minus of 1 joules per mole of it. Right? So you can see this is how you can do this type of the questions. Okay. So the answer becomes 2 into 10 to the power of minus of 1. C is the right answer in this case. Okay. Next, this question now. Among the following, the correct thermodynamic equation of the state is, we know very easy now, del U by the del V at constant temperature. So again, I'm gonna go from the basics. We are remembering the equation, that is very good, but if sometimes you forget it, you should know the derivation part of it so that within a few seconds you can solve, you can reach up to that final equation. So it is good. People have studied under very amazing teachers. So now du value, you know, it is dependent upon the ds and it is dependent upon the dv. Opposite of the entropy you are having is this temperature, the arrow is going towards the temperature. So it will be positive, that is TDS. Now, opposite this other term we have written is the volume. So opposite of the volume, it is the pressure, arrow is going away from it. So it will be minus of the PdV of it, right? So now I have to differentiate it with respect to the volume, del U by the del V. So del U by the del V at the constant of the temperature. So it will be temperature into the del S upon the del V at the constant of the temperature minus of the pressure into the del V by the del V at the constant of temperature. This is unity only, right? So now this is coming as temperature into the del S by the del V at the constant of temperature minus of the pressure, right? So now you can see in the units of del S by the del V, I'm not having any expression. So again, one more relation for the Maxwell square, I'll be using it. So we are going from del S by the del V. So this value it is there, del S by the del V. The opposite of the entropy is the temperature, arrow is going towards it, so positive. This is equal to this value, del P by the del P by the del P. Now opposite of the pressure you are having the volume, so that it will be included. So this substitution we can make it. So this will be equal to temperature into the del P by the del P at the constant of the volume minus of the pressure. So this is my del U by the del V at the constant of the temperature. So the complete derivation part I have also shown you. So if you remember the first thermodynamic equation of state, well and good. If not, you can do it, or you can also do it like this. Okay, so temperature into the del P by the del T at the constant of the volume minus of the pressure. Option B, it is the right answer. Okay, next. This one, the change in the entropy and the gives free energy for a system, it is denoted by delta S and the delta G respectively. Okay, for a reversible melting of the ice. So what is happening? Ice is melting from the solid. We are going to the liquid of it, right? So solid ice it is there. So ice and the water, they are in equilibrium. The temperature is also given, which is 1 atm and the 0 degree centigrade. So this condition, which is 1 atm and 0 degree centigrade, it is for the phase transition. It is for the phase transition and the system, it is in the equilibrium. It is in the equilibrium, and at equilibrium we know delta G value, it is gonna be 0 only, and the entropy change. So from the solid you are converting to the liquid. So entropy, that is degree of the randomness, it is gonna be increasing. So this is gonna be increasing, right? So delta S is greater than 0, delta G is 0. That is option B, it is given. So option B becomes the right answer. Okay. Next, this question now. The thermodynamic variable x in this equation. So del S by the del P at constant temperature. So now here you see del H by the del P at constant temperature, which means something related to the second thermodynamic equation of state it is there. Right. So again we will be starting from the basics. That is, good people have studied under very amazing teachers. Now for the enthalpy change, you have to write the Maxwell relation dH. So on the upside of this enthalpy, you are having this entropy and the pressure term. That is dependent upon the entropy and it is dependent upon the pressure term. Now opposite of the entropy you are having is this temperature. Arrow is going towards it, so it will be TDS, and the pressure opposite of that, it is the volume, so it will become the plus of the VdP. Now del H by the del P, you have to find it, differentiate it. So del H by the del P at the constant of the temperature, it is temperature. Now it is del S by the del P at the constant of the temperature plus of the volume into the del P by the del P at the constant of the temperature. So this becomes the unity only, right? So from this we are getting that del H by the del P at the constant of the temperature, it is temperature into the del S upon the del P at the constant of temperature plus of the volume. So now from the given equation here it is del S by the del P at constant temperature. So this value just find it out. So we are getting del S by the del P at the constant of the temperature. This is gonna be minus of the volume plus of the del H by the del P at the constant of the temperature, and all of this will be 1 by P, it will be common. Alright. So now equating it to the given expression, which is del H by the del P at the constant of temperature, it is 1 by T into the X plus of the del H by the del P at the constant of the temperature. Equating this, you are seeing X value we are getting, that is minus of PV, right? So from here my X is minus of the volume. So this is the correct answer. That becomes the option C to be the right answer. Okay, next this one now. So again the figure has been given. Total amount of the work done in this cyclic process we have to find it out. So firstly see, we are going from A to B, that is this direction, and we are going in this. That means we are going in the anti-clockwise direction. It is in the anti-clockwise direction, and the work done in the anti-clockwise direction, it is positive. From this, here you can eliminate the option number third, that is given negative work. So if it would have been the clockwise, then the negative work it would have been done. Okay, and one more option you can eliminate, because under the area under the PV work, PV curve, it gives us the total amount of the work done. So some area you are seeing that it is getting being covered, so work done it cannot be zero in this case, right? So here area under the PV curve, it tells us the total work done. It gives us the total work done. Right. Now in this process, it is this triangular shape we are getting, A to B, B to C, and the C to A. So it is here in this, the total amount of the work done, it is gonna be half into the base into the height of it, because this triangular it is becoming, so that is gonna be half. Now the base value, that is from B to C we are going, so it is 3V1 minus of the V1, 3V1 minus of the V1, and the height we are having, that is from the A to B we are going. So it is 7P1 minus 7P1 and the 6P1 it is there. Right. So it is 7P1 minus of the P1. Right. This value it is becoming. So this is gonna be equal to half into the 2V1 into the 6P1 of it. So this 2 gets cancelled. So work done, it is 6P1 into the V1 of it. This is gonna be the work done. So that makes the option A to be the right answer in this. Right. So A is the correct answer. Next, this question now. The application of the Euler's reciprocity relation, which is cross derivative rule, to the volume of 1 mole of the ideal gas in a mixed second derivative of the volume is equal to. So firstly, it has n value, it is 1 in this case, and the gas it is ideal, which means PV is equal to the RT only we will be applying. The mixed second derivative of the volume you have to find it, which means the volume differentiation you have to do it two times. Okay, one with respect to the pressure and one with respect to the temperature you have to do it. So now here PV is equal to the RT. From this volume it is equal to RT upon the P. So first time differentiate it with respect to the temperature. So del V by the del T at the constant of the pressure, this is gonna be del by del T of volume, it is RT upon the P. This differentiation we are doing at the constant of the pressure. So R upon the P, it will come outside. It will be del T by the del T. At the constant of pressure, this is unity only. So we are getting here the value which is R by P. So now this expression that you have obtained it, which is of the del V by the del T at the constant of pressure which is R upon the P. So again now differentiate it with respect to the pressure now. So here we will be getting del by the del P of T, del V by the del T at the constant of the pressure, at the constant temperature we are doing it. So it will be del by the del P of the R upon the P. That becomes, so this differentiation is done at constant temperature. So this becomes minus of the R upon the P square. So you can see double derivative of the volume we have done it. So at first at the pressure, then at the temperature, or first at the temperature, then at the pressure, then you will be doing again same value you will be getting, because here the Euler's theorem it is getting the obeyed over here, because volume it is your state function, right? So here firstly if you do the differentiation with respect to temperature, then also you will be getting the same values, that means this thing del by the del P into the del V by the del P at the constant of the temperature. This will be done, and this has done at the constant pressure. This is also gonna be minus of the R by P square. So Euler's reciprocity is being obeyed. Okay. So that makes minus of the R upon the P square as the value. Option first one is only the right answer. Okay. Next, this question now. The ideal gas undergoes the isothermal expansion from the volume V1 to V2 in two different ways. First is by reversibly. Reversibly means slowly we are removing the weight from it, and at any point of time you can reverse the process. And irreversibly means abruptly we are removing the weight from it. The correct statement in this, so we know work done always for a reversible process it is more as compared to the work done for the irreversible processes. This condition it is always the true one, right? So here you can take the magnitudes of this also, they are always gonna be greater one, right? Now since the process it is isothermal, so temperature we have kept to be the fixed. Now internal energy we know it is function of the temperature only for the ideal gases. So that means delta U for this it is gonna be equal to the 0, right? Now from the first law delta U it is Q plus of the W in this. So delta U it is 0. So this is Q plus of W, which implies work done it is minus of the Q of it, or the Q it is minus of the W of it, right? So we can say this thing that work done for the reversible process it is more as compared to the work done for the irreversible. So if you take the negative signs also, now here the magnitude it is there, so no impact, so this only value will be there. So we can say that it is Q reversible is also greater than that of the Q irreversible. Their magnitude also you can take. So again, you can see we are getting the same conditions which says Q reversible is also greater than the Q irreversible, and the work done for the reversible is also greater than that of the irreversible. So from the given ones, W reversible greater than the Q, this one, but here it is less, incorrect one. Work done for the reversible is more, and here also it is saying reversible it is more than that of irreversible. Option B will be the right answer. Okay, next. The variation of the molar heat capacity at constant volume, it is with the temperature of the gaseous diatomic. So the gas is diatomic is shown in the diagram below. The values of the x, y and the z respectively are. So this is your x value. So this value it is 1.5 bar it has been given. After that you are having, this is your x value. This value somewhere around the y you are having, and this is at the z you are having. So you can see as the temperature it is increasing, the values of x, y and the z also it is changing. X is the one that is at the low temperature, and the Z value that I am having, this one, this is at the highest temperature. So this is at the high temperature, right? So CV value, it is varying with these temperature values. So now we know that gas, it was diatomic, right? So the number of atoms in it, it is 2, right? So the total degrees of freedom in this you have total degrees of freedom, that is 3n, which is 3 into the 2, which is equal to the 6. Now degrees of freedom means the number of ways in which the particles they can rearrange their energy, right? Now to rearrange this energy, the particles will be having the translational degrees of freedom, translational degrees of freedom, they will be having the rotational, and they will be having the vibrational degrees of freedom. Okay, out of these six, three we have the translational, two we have the rotational. Now the vibrational degrees of freedom, it is dependent upon the temperature, whether its contribution it will be taken or it will be not taken into the account. Okay, the vibrational, it contributes only at the high temperature. At the high temperature contribution is there, but at the low temperature contribution of it is not there. Okay. At the high temperature contribution is only of the 1 degree of freedom, but at the low temperature we are not taking its contribution. Right. So that means it is gonna be varying. Now the internal energy you find it. So this is at the low temperature if you find it. So that is gonna be now three translational degrees of freedom we have. So total it is three. Contribution per translational degree of freedom, it is RT by the 2, right? Plus of the rotational ones you are having, which is 2. Now contribution is again RT upon the 2 of it. So this value it comes out to be as 5 by the 2 RT of it. So this is the delta U you have it. Now CV we know the delta U it is NCV into the dt of it. So CV value it is delta U by the dt of it. That means with respect to temperature you have to divide it. So that means we are going to get the value of the 5 by 2 R in this case, which is my 2.5 R value of the CV I'm gonna get. That is at the low temperature, right? So at the low temperature the value is of the X we are having. This is what the CV value we are having, right? So that means at the low temperature, the X value it is gonna be 2.5 R only. So from the options you see, 2.5 R value it is given to us in the option second only. So this is gonna be our correct answer. I hope the concept it is clear. At the high temperature also we can see it at the high temperature. So here three translational degrees of freedom, contribution per each it is RT by the 2, two rotational degrees of freedom, contribution it is again RT by the 2. Now the vibrational degree of freedom that is 1, contribution it is RT over here, right? So total internal energy you find it, that is 7 by 2 RT of this, right? This is delta U. CV value it is gonna be 7 by the 2 R in this, which has the value which is my 3.5 R in this. So this is the maximum value, right? So that is maximum value which is at the highest temperature, that is at the Z corresponding to Z we are having. So that means Z value is 3.5 R. So you can see in this option 3.5 R which is corresponding to my Z value. The y it is lying in between these two, so it has obtained the value of the 3R. Okay, so this is how this question it was to be solved. So this question now, it says 1 mole of a monoatomic. Now firstly, number of the moles we are having, that is 1 of a monoatomic gas. The gas is monoatomic. It is at a 1 atmospheric pressure. It undergoes the compression from 49.2 liters to 24.6 liters under the reversible adiabatic conditions. Reversible adiabatic conditions. The final temperature. So reversible adiabatic here it means the Poisson's equation it will be obeyed. Poisson's equation it will be obeyed in this case. Now here it is saying the final temperature. So we can use the equation which is PV gamma minus 1 it is constant in this, right? That means we need is P1 V1 gamma minus 1 it is equal to T2 V2 gamma minus of T1. From this T2 we can find it out, which is T1 into the V1 upon the V2 raised to the power of gamma minus 1. Right. So now the volume conditions, which is V1 and V2, you are having it, but the temperature, initial temperature, you are not having it. That too you have to find it out. But we have been given that number of moles, it is 1. The 1 atmospheric pressure is there, and the initial volume also we are having. So using these conditions, because the gas is ideal, using these conditions we can find the T1 temperature firstly. So let's find that. So T1 temperature, PV1, T1V1 is equal to the N R into the T1. Right, number of moles is 1, R it is 8.314, or depending upon the P and the we will be keeping this. So it is the R into the T1. The volume, it is pressure we have been given, that is 1 atm, and the volume we have been given, that is 49.2 liters. 49.2 liters of it. From this, the temperature, it is gonna be 1 atm, or the 49.2 liter atm value it is there. Now the R value you have to keep it in the units of this only. So this is 1 mole we are having into 0.0821 liter atm per mole per Kelvin, per mole per Kelvin. So the units here you see, this per mole and the mole unit will cancel out. Liter atm will get cancelled out. Solve this and find your temperature. Okay, so T1 value you can get it from this one. So T1 we will be getting, that is 599.27. So this is 599.27 Kelvins. So this is the temperature T1 we have got it. Now this T2 value we can find it because rest conditions we were already having it. So now T2 value, this was equal to T1 into the this was V2, V1 upon the V2, V1 upon the V2 raised to the power of gamma minus 1. The atomicity of the gas is also given, which is monoatomic. So gamma value we are already knowing it, that is gonna be 5/3. Right. So at temperature 1, we have found it as 59.27. The volume V1 we were having, that is 49.2. The final we are going to 24.6 liter. Gamma value it is 5/3 minus of the 1. Just solve this now. This becomes your 2 over here, right? So 2 raised to the power of 2/3, 2 raised to the power of 2/3 into the 599.27. This gives us the value of 951.28 Kelvins. This is the temperature T2 you are having it. Okay. That means the correct answer will be the option 1, that is 952 Kelvins. Okay. Next, this question now. The standard Gibbs free energy, it refers to the Gibbs free energy. This is at any temperature, but the pressure we have to keep it as 1 bar. Temperature is not always 25. It can be at any temperature and at 1 bar pressure. Option third is the right answer for this. Okay. Next, this question now. 1 mole of the monoatomic gas. So number of the moles, it is 1 in this. The gas, it is monoatomic, is taken through a PV cycle, which is as shown below. First, second, and the third has been given. The volume and the liters is given. For the process which is 1 to 2, the reversible work done and the change in enthalpy respectively are. So for the process which is 1 to 2, this process we are going. So you see, during the 1 to 2 process, pressure is keeping to be the constant, which means it is your isobaric process. Right. So for the isobaric process, work done, it is minus of the P external into the dV, which is V2 minus of the V1 of it. Now in this external pressure, it is 1 atm only. Now the volume V2, from the 1 to 2 we are doing. The final volume, it is 44.8 liters of it. The initial one, it was 22.4 liters of it. Right. So this we are getting, that is 22.4 liter ATM, liter ATM. the work which is being done, right? So this is minus of it. So minus of 22.4 liter ATM. We have to find in the units of the kilojoules of it, right? So again the conversion will be done 22.4 liter ATM into 8.314 in the units of joule per mole per Kelvin divided with the 1 in which the liter ATM we get it, that is 0.0821 liter ATM per mole per Kelvin, per mole per Kelvin. So you see here the common terms which are getting being cancelled. Units of mole per mole and per Kelvin and per Kelvin, liter ATM and liter ATM. So units are becoming of the joule only, right? So here we get the value which is now in the kilojoules we need to find it. So divided with the factor of the 1000 also. So you will be getting in the kilojoules, that is minus of the 2.27 kilojoules you will be getting it. Okay. So that makes the option second and the third to be eliminating. Answer is gonna be from the one and the fourth one. Now the next thing we are asked to find is the enthalpy value, right? So now the enthalpy, that is delta H, we know it is NCP into the dt of it. It is function of the temperature only. So that means we need is NCP T2 minus of the T1. So temperatures is needed at the this conditions, that is at the first and at the second conditions, right? So at the first condition, firstly T1 temperature we can find it using the ideal gas equation, which is gonna be T1 V1 is equal to the nR T1. So T1 it is equal to P1 V1 upon the nR of it. Now here the pressure at the first condition it is again the 1 atm. Volume here it is 22.4, right? So it is 1 into 22.4 units, it will be a liter ATM. So number of moles is 1, it will be 0.0821 liter ATM per mole per Kelvin, per mole per Kelvin. Okay. So here you see, so here n, this was the number of the moles. So mole and per mole per Kelvin, sorry, this Kelvin units we will be getting. These units which is of liter ATM and liter ATM is getting being cancelled out. So temperature it comes out to be as 273 Kelvins. Similarly T2 we have to find it. So T2 it is gonna be T2 V2 upon the nR. Again the pressure here it is 1 atm. The volume here it is now 44.8 liters of it. The N is again the 1 mole of it, and the R value it is 0.0821 liter atm per mole per Kelvin of it. Right. So with this mole per mole, liter atm and liter atm it will get cancelled over here. So Kelvin temperature you will be getting, which is 546 Kelvins. So temperature T1 and T2 you have got it. Number of moles it was 1. Now the gas it was monoatomic. So for the monoatomic gases, Cp value it is 5 by 2 R. It is 5 by 2 R of it. Temperature it is 546 minus of the 273 Kelvins of it. So we are getting 5 by D2 in the units of 8.314 into the joules. This is in the joules per mole per Kelvin, and here it was 1 mole, right? And the temperature difference it is 273 Kelvins of it. So we are getting this Kelvin, you can keep like this or this one. So this Kelvin and per Kelvin, this mole and per mole term will get cancelled. We are getting the answer in the joules of it, divided with the factor of the 1000 to find your answer in the kilojoules. So we will be getting, that is 5.67 kilojoules. So this is gonna be the delta H value. Okay, this is my answer. That makes the 5.61, that is the option first one to be the right answer. Next. So this was the last question that was from the topic, which was your chemical thermodynamics. So from the year 2011 to the year 2025, all the questions of the chemical thermodynamics we are done with this. Okay. So I hope all these questions they are clear to you. If you still have doubted any of the equations, that you can ask me in the comment section. I'll surely reply to that. Okay, and if you have understood the concepts, then make sure you like the video and do share it with your friends as well. And if you have not subscribed to the channel so far, make sure you subscribe to the channel also, because many more questions and many more chapters we are gonna discuss. Okay, so thank you so much for this one. We'll be meeting you in some new video now.